Hi everyone, I'm Vicky, and today I'm presenting our work on space, time, and choice on behalf of myself and my collaborators Elaine, Karan, and Vandy at the University of Toronto. Our work is about personal planning, so let's see what that looks like. Imagine I have an appointment with my financial advisor that I'll go to straight from work. If I bike there, it'll take 12 minutes. There's probably enough time afterwards for me to pick up food for the picnic later. Some fruit maybe from La Fontaine's Farmers Market, or maybe I should get fresh baked goods instead. You know, a big bottle of cold brew tea from Matcha would be really great right now. I should try to be at the picnic by 5 though. These are screenshots of me ping-ponging through Google Maps, which may suffice to satisfy my planning needs, but I don't actually have a clear visual of my time. It's hard to make direct comparisons between options, and I lose all my work. Though these bits and pieces of routes add up to a schedule, there's no way for me to actually turn them into one. This is the kind of location-based personal schedule creation and exploration that we aim to support through our research. Recognizing that our lives are planned in both space and time, we seek to bridge the gap between route mapping and time scheduling tools to support a general purpose spatiotemporal planning workflow. Now let me show you how we can make this process effective using our approach. Here I see all the timings and the locations in context, including all the different travel times and respective event durations. And I can experiment with adding the tea shop or the bakery to my schedule. Or I can compare all my different options in context in a flexible manner. We'll get back to the prototype later. What I hope you caught from this quick overview is that our workflow accommodates flexible planning and a direct manipulation interface that also supports space-time reasoning. Let's see the foundations behind our approach. To unpack what flexible personal planning entails, we developed a framework that captures the factors involved in planning and how these are impacted by changes in plans. Planning is the attempt to satisfy some set of motives by allocating adequate time and determining an available environment through which these motives can be fulfilled. It's an interplay between requirements defined by the user and externally enforced restrictions. The sum of these we call our space-time constraints, which are the input to our space-time planning workflow. Let's consider my motives from earlier. I want to go to my bank appointment at 3 and then stop by some place to pick up treats, to be at the picnic by 5. My requirements are to see my financial advisor, obtain some fresh snacks, and arrive at the picnic by 5 p.m. Some externally defined restrictions are the hours of operation of the locations I want to visit, the schedule of my financial advisor, and travel times between locations. These constraints fall along various spectrums. They have some degree of spatiality, temporality, or both. Importantly, they often express some degree of flexibility. For example, my appointment at the bank has fully fixed temporal and spatial requirements, but getting snacks involves a semi-flexible spatial requirement, as several potential locations can satisfy my motive. Now with the constraints defined, we can complete the space-time planning workflow. The aggregated requirements and restrictions can have one of 3 outcomes: an under-constrained set of schedules, an over-constrained lack of schedule, or a single solution. One way to reach a final single solution is to use automated optimizations, leaving it to the system to prioritize or relax different criteria. Another approach is to leave it up to the users themselves, to reevaluate their own motives, considering preferences, trade-offs, or compromises, and to recreate the requirements in a potentially iterative process. We posit that a hybrid approach is optimal, providing users with assistance, but ultimately supporting them in making their own decisions. Sometimes user subjectivities just don't easily fit as input into algorithms, but users should still have the opportunity to leverage them on their own terms. Note also that both external restrictions and user motives are prone to change at any time. A space-time planning system should be robust to such changes. We distilled our framework into design goals for tools in practice. First, to support spatiotemporal reasoning, primarily using visualization. Second, to enable workflow flexibility. Third, to minimize busy work via both ease of input and use of automation. And fourth, to all the while maintain user agency, leveraging technology without sacrificing user control. We implemented core features of our space-time planning workflow in a space-time planner prototype tool that runs on mobile devices. Drag a place from the place palette to the schedule, and it shows up in the map. Notice that the hours of operation are visible in context, and that travel time updates automatically update in the schedule too. We prioritize travel time in this implementation by preventing conflicts through the pushing feature. Now, let's see something a little less defined than the locations currently in our schedule. Remember, we're not yet sure of which of the places we'd like to grab treats from. Our tool includes a group mechanism, the one-of group, which allows us to indicate to the system that any of these locations would work and one would be enough. In other words, the one-of group represents both flexibility and mutual exclusivity between a set of candidate locations. By default, we set up these groups to automatically select the option that results in the least travel time, even during future schedule updates. The group can also be used to make comparisons between locations within context of the schedule, and the manual selection can be locked in at any time. Group constructs like the one-of group we just saw represent shared or related requirements among a group of locations. Let's imagine that in my scenario, I actually have a bit more time before the picnic, and so I want to visit as many of the listed locations to put together a real feast. Another type of group, the as many of group, is useful for when you have a list of things to do of roughly similar priority, like a list of errands or tourist attractions, and you want to fit in as many of these as possible. As we drag the group or modify its duration, the auto-optimization picks the solution that maximizes the number of visited locations while minimizing travel time, though it would be trivial to consider other algorithms to prioritize solutions. And of course, the as many of group also allows manual exploration of the different solutions. We conducted a user evaluation to gather feedback on the space-time planning concept and prototype. It included a structured replication task and a freeform task in which we asked participants to create a travel itinerary for a friend and a city of their choice. Participants were able to complete the task successfully, creating rich schedules such as these for the freeform tasks in a number of minutes. I'll go over some highlights from the study, reflecting on our goals, but you can find more in the paper. We found that participants valued the unified spatiotemporal visualizations and workflow while completing the tasks, indicating that, for example, it increased their conceptualization of the actual time they had available when creating multi-destination plans. We also witnessed participants take a variety of different approaches to schedule building. Most liked to create a skeleton that they were then able to modify, tweak, and reevaluate as they went. Some had a highly iterative approach, experimenting with dragging and dropping events and taking the system's calculated solutions as suggestions. With respect to automation, participants appreciated the assistance from the computer in doing calculations for them. But they also highly valued the level of agency they had over their planning. They commented not to move towards a more automated or more manual system overall, but rather to increase capacities in both directions, described by one participant as fine-tuned control over automation, which we find very exciting in this avenue of research. There is much great work out there on the automation side of things. Solvers for multi-criteria decision-making problems that could hopefully be integrated into the vision we share here. What we believe requires additional attention in HCI is to continue improving the interaction designs that will best alleviate friction in this human-computer collaborative process. Our work focuses on establishing a unified and user-centered space-time planning ideology. We dive particularly into the user-motivated aspects of the workflow, and already envision many ways that our work thus far can be extended. There is much to do in expanding the supported space-time requirement vocabulary, adding just-in-time conflict resolution, and working across larger space and time scales. Please check out the paper for mock-ups and additional scenarios, like that of a film set assistant whose space-time schedule is constantly challenged by her demanding job. With that, I thank you for your attention, and I'm happy to take questions.